Hello everyone, myself Dr. Vasudeva Reddy. I am working as Associate Professor in the Department of ECE, B.V. Raju Institute of Technology, Narsapur. Today, I am going to discuss about introduction to VLSI and its design flow and its applications, advantages and so on. So coming to the subject, the prerequisite to the subject is electronic circuits and devices and digital logic design. So these are the basic two subjects that are required for studying VLSI design. So these two subjects students are studying in their curriculum. Coming to course objectives, interpret different steps involved in fabrication of integrated circuits, analyze the behavior of inverters designed with various loads, and also develop the layouts for various digital logic design circuits, and implementing the logic circuits using different types of CMOS technologies, and implement the relevant concepts as per their academic projects. And after completion of the course, students are able to interpret different steps involved in the fabrication, different types of behaviors, and especially these things will be useful when they are doing academic projects as per their curriculum, and also they will be knowing some of the important things which are required by the industry. Coming to industries that they are offering internships as well as jobs for the engineering students who are studying or who has a VLSI subject as their in academics are Waferspace, Intel, Synopsys, Cadence, NVIDIA, Analog Devices, Xilinx, Texas Instruments, Micron, Microchip, Bosch, Cypress, Microsemi, Sankalp Semiconductors, Wipro, Digital Core, Arisent, Avantel, Tata Technologies, Path Partner, Ensilica, Alexi, Arise, Baker Hughes, and Skyworks, Avago, Tech Mahindra, Qualcomm, Broadcom, and so on. So these are the different companies that are offering the jobs for especially engineering students who are familiar with VLSI knowledge. Coming to jobs, and they have different types of roles in the industry. One is a front-end design engineer who will be working on Verilog as well as VHDL codes, and also verification engineer for their design to verify models, and physical design engineer who is working in the back end and they will be working on the layouts designs for their requirements. And coming to mask layout engineers and layout, as a layout engineer they need to verify different types of design rules, and they will be taking as a design engineer in the mask layouts models. And next, DFT engineers, design for testability engineers. In order to know the functionality of the design accurately, those people are working as a design engineer in the DFT roles. Post silicon validation engineer, who is the main person for verifying the silicon designs and layouts as their role. And coming to analog and mixed design engineers, who will be familiar with analog designs as well as digital designs, and they will be implementing different types of models as per their requirements. And finally, FPGA engineers. And these are the different roles that the companies are offering for the students or the engineers who is familiar with VLSI knowledge. The coming to textbooks that are as per their academics are Herman Douglas Bucknell, Wayne Wolf, Neil Weiste, and FinFET Devices by Saha. And coming to reference textbooks, John Oimera and SMZ for VLSI technology, and Med and Conway, Introduction to VLSI Design by BS Publications. And coming to smart products, nowadays whatever we are using right now, those are, as you know, smartwatches. So it consisting of, nowadays we are considering different types of health parameters basically, And those, in order to grab those different base health parameters, we need to have number of sensors, and all those number of sensors are integrated in a electronic equipment that is nothing but your smartwatch, where these number of circuits or the sensors which are integrated with a integrated design model, which is nothing but a smartwatch. And also the camera, smartphones with cameras with number of designs. And coming to smart cities culture, where number of devices are interconnected together like routers, switches, and so on, so that we are able to make convenient our life easy. And not only that, some of the speakers, Bluetooth speakers, and which we are able to interact with the devices directly, so that the sound can be heard instantaneously. So it means to say that, and not only that, fridges and smart home systems. So in all the way, the products whatever we are using in our daily life, consisting of millions of integrated circuits, where it is basically a composed of a software as well as hardware, where the software comes under or VHDL, where the hardware comes under different types of design models. And also some of the other examples, if you see, mobile phones, which consisting of different types of integrated circuits for different applications, and routers. So we have routers in our home, which the data can be encrypted and decrypted, and in order to do the processing of such type of applications, we need to go with a router which can be composed with a number of integrated circuits. And also smart TVs, where earlier days we used to have a box kind of TVs, whereas now the entire system is, due to the technology advancements, it has come down to a stage where we have a curved TVs. So therefore, in order to make all these functionalities like encoders, decoders, amplifiers, switches, and all those things, all these connections are integrated together and made as a simple curved structure of TV, and that can be seen in our daily home. Not only that, amplifiers and radar systems, as well as micro ovens, and so on. And nowadays there are n number of vehicles in the market, where they're coming with number of sensors, which is a major role even to control or to have a efficient model of the design. So here you can see a model where it is occupying with a number of sensors like AC sensors, rear camera, fuel. You have different types of sensors. In order to control all these different types of sensors, we need to have an integrator circuit, where that integrated circuit will be taking the inputs from different sensors and doing a functionality and sending the information to somewhere else, or it is going to store in certain database. So this is a simple example. Nowadays, a motor vehicle which comes with number of vehicles nowadays. And also if you see a smart product like routers, controllers, gateways, networking designs, firewalls, and all those things, which comes under a internet model, where it consisting of number of integrated circuits, where all these circuits are based on the number of inputs as well as outputs, and also for doing multiple functionalities in a certain sort of applications, will be going with such kind of things. And behind all these things, a basic element that is required for a switching operations is NMOS or PMOS or CMOS technologies. If you see any kind of operation in the universe which comes with a switching, so we can say that here a basic switching functionalities can be performed with NMOS or PMOS or CMOS devices. So considering NMOS turns on when the voltage is at higher and off when the voltage is at lower position. So when the input voltage is high, then the NMOS transistor is going to switch on. When the input signal is low, then we can say that it is acting like a off switch. And the same thing inverse for PMOS transistor, it makes on when the device is under lower voltage. At the same time, PMOS is off when the device is under high. So it means, so a combination of these two things, a PMOS as well as NMOS, is treated as a complementary metal oxide semiconductor, where one device is in on when one device, that is NMOS device, is in on state, PMOS device is in off state, and vice versa is happening whenever you are processing a certain sort of designs with help of CMOS technology. So the majority charge carriers in NMOS is electrons, whereas minority charge carriers are holes. As well as for PMOS, the majority charge carriers are holes, and NMOS, the minority charge carriers are electrons. But the current conduction is due to electrons. So as the number of electrons are low in PMOS, the size of the PMOS is more compared with NMOS design. And considering NMOS and PMOS combined together, then we can say it is acting like a CMOS design models. So here we can see NMOS as well as PMOS structure, and we can observe how it is acting like. So NMOS design, as well as where the indication, arrow mark indication indicates the moment of electrons which is moving outside, whereas P, you can say this, a PMOS which is accepting the number of electron holes which is inside to that. So a combination of PMOS and NMOS, which we can treat it as a CMOS. And logic diagram, if you see, a PMOS which is treated as pull up transistor and pull down is considered as NMOS. So considering A is the input signal for both gate terminal, and taking the combined point Y, whenever you have applied A to this, so when A equal to 0, a complement input is applied to at the gate, then this is acting like closed switch. There is a channel between gate and the substrate, so this gets filled. Then the sum of the voltage that you are applying from VDD, which pass through the voltage, and they will be producing the output. So it means whenever you are applying 0 here, there will be a current conduction across this, then we will be getting a output across Y, which is equal to 1. Same thing, so during that state, this NMOS is acting like a off switch. And when 1 we apply, so as it is complementary 1, this is a channel is open, so this is acting like open switch, and during that state NMOS is on. So whatever the voltage that we have here, that will go towards the NMOS, and that will be producing output as 0 volts. So here you can see the symbol of inverter circuit, where 1 you apply, 0 you get, when 0 you apply, 1 we get. Okay, so this is the basic component. In order to design any kind of circuit, we are going with. And so as it is considering the inverter circuit is the basic model for an integrated circuit, we are going to consider number of transistors together to form an integrated circuit. So what exactly the meant of integrated circuit? A complex set of electronic components which are of tiny transistor in a small chip, and their interconnections that are imprinted on a tiny silicon semiconductor material. So on top of silicon semiconductor material, we are forming a number of tiny transistors, and those transistors are combined together to make a integrated circuit. Coming to different types of MOS technologies, we can classify it into different types. The one is bipolar. So BJT models comes under bipolar technologies. Then next one is CMOS technology, complementary metal oxide semiconductor devices. A combination of bipolar as well as CMOS can be treated as BiCMOS. then silicon on insulator, and the next one is silicon and germanium, and next model is gallium arsenide. And why we need to go with CMOS design? The basic advantage with CMOS design is low power, then high package density, scale down to more easily, fully restored to logic levels, equal arise and fall time. So it means to say that when we compare with BJT models, obviously the amount of power consumption which is consumed by the design, which is very less. Next, we can incorporate more number of components into it for multiple functionalities. We can scale down it to larger way so that multiple functionalities can be defined. At the same time, we can go to a lower values of channel length so that we can integrate more number of components into it. So equal fall and rise time, which is the major advantage of CMOS technology. Right? So if you see the basic comparison between BJT and CMOS, power dissipation is moderately high in this case, whereas CMOS case it is well less. And when it comes to speed, BJT is comparatively faster, but whereas CMOS is fast. And transconductance is 4 ms and 0.4 ms, and switching implementation is poor in BJT case. And whereas CMOS case, this is the advantage. And when it comes to technology improvements, it is slower in design, whereas this is faster in design. And you can see here scale of integration. When it comes to scale of integration, the number of components that we can accommodate in small scale integration is up to 64 number of transistors. Whereas when it comes to medium scale integration, it is up to 2000. Whereas large scale integration, it is up to 64,000 number of transistors which are accommodated. And coming to VLSI, 2 lakhs gates that we can accommodate. And ultra large scale, you can have more than that value. And coming to IC technology, we can say that the number of transistors that we can have here maybe more than 1 million, 2 millions and so on, based on the requirement of the design. And coming to types of integrated circuit, we can classify basically it into 2 types. The first one is linear or analog integrated circuit. The second one is digital integrated circuit. Coming to examples of linear integrated circuits, we can say the one is op-amp, power amplifiers, multipliers, comparators and regulators. So all these things comes under linear or analog models, where the input is in the form of voltage. Whereas when it comes to digital integrated circuits, it has that operates with a digital signal, and some of the examples are logic gates, flip-flops, counters, calculator chips, memory designs and processors. So based on the requirement, you may choose either analog or digital integrated circuits, where the analog circuit is taking analog signal as input, where digital integrated circuits are considering digital signals are the inputs. Coming to design flow, we have here a design flow where the first step in the design flow is design specifications. So here as a design engineer, you need to consider the basic step, which is specifications. So the specifications comes from the customer where and what exactly he is expecting. So that is treated as initially the specification. As a design engineer, apart from the customer specifications, you need to add some of the other parameters like area, power and delay or speed. So first, considering a design specifications from the customer, as a design engineer, we are going to write a program in the high level language. So we are describing the requirement of the customer in the form of logical model. That is nothing but behavioral description. So we, as a design engineer, will be writing a code that is in the form of either Verilog or VHDL, and that is the first step when it comes to logical model. So then the behavioral description is converted into RTL description, register transfer logic, and here the entire logic whatever you have described in the behavioral model is treated in the form of register transfer logic. So the entire model is treated as black boxes, and those number of boxes are connected together. Then it comes to verification part. So considering each functionality is in the form of register, then we'll be going to describe its functionality by applying different combinations of inputs. Then we are going for verifying the functionality. Once if it is proven, then we are moving on to next stage. If not, we are going to test again and again in the same place. So we are going back and we are considering whether we have taken the right inputs or not, whether we have chosen the right design of the RTL or not. If not, we will be modifying some of the designs in the RTL design. Then again we are going for verification of it. Then we are going for testing. Once if it is proving in all the way result, then we are moving on to logic synthesis and timing verification. The next step of functional verification and testing is logic synthesis. We are verifying the logic functionality and its timing accurately. So in order to process exactly the logic synthesis which is equivalent to the previous design, as well as whether it is meeting the timing requirements, we will be going for again verification of it. Once it is proving the result, then we are moving on to gate netlist. So same logic is described with the number of gates and which are connected with the number of interconnections. So that is nothing but gate level netlist. Once after finishing the gate level netlist, again we are going for verification of it and going for testing of it. Once if it is proven, then we are moving on to logical verification and testing. Logically, it has to prove the result based on the design or the function that the customer is expecting. Then we are moving on to the floor planning, automatic placing and routing. So here we will be considering floor planning, which is more than a requirement for further use. In case the customer wants more and more applications in future, then we can say that some of the extra space which we are including in the design so that it can be used for further use. Then finally we are moving on to physical layout and we are going for testing of it. So placing of all the components at different places, making an interconnection across it and verifying its functionality will be giving you exact layout verification. Then implementation. Finally we are going with implementing this design in the form of GDS II model. So in any of the part, if we feel it is not satisfying the customer requirement, and also the secondary aspects like power, area and delay, if these things are not proving, then we are going back and verifying in each model, and then we are going to resolve that issue, and then again we are going for verification of it, testing the functionality in terms of timing and placing, again layout verification and so on. So this approach is called top-down approach. So top-down approach is nothing but you have a system, that system is dividing into number of subsystems, where subsystems are divided into number of subsystems and so on. So what is happening is a single system is divided into number of subsystems and number of subsystems are divided into subsystems. Finally, we are coming to a conclusion where the leaf model, final model cannot be split it into further levels. This is nothing but top-down approach. This is the design that the design engineers are following in the industry. And here you can see there are two types of models. One is front-end design, where the functionality is proven in the form of software model using different types of tools. Whereas when it comes to back-end design, the entire design is dumped onto the integrated circuit, which is in the form of hardware. Then we are evaluating its functionality. So this is nothing but back-end process. So this is front-end design and back-end design. So if you see the structure of integrated circuit, basically as we know, system specifications is the initial step, architectural design, and it has to prove the functionality as well as its properties, and also circuit design, physical design, layout verification and sign off, and finally we are going for fabrication on integrated circuit, which is on silicon wafer. Finally we are going for packaging and testing, and finally there is a made of integrated circuits. So here you can see this is the top model where this is divided into number of entities, and again this is divided with the number of subcomponents, and each component is having number of sub models, and we are following different types of design rules like LVS, DRC and ERC rules, and the same thing is dumped onto the integrated circuit, which is in the form of silicon wafer. And finally we are going for packaging and testing. Once it is proven, then finally you can say that the integrated circuit is ready for use. And coming to some of the advantages of integrated circuit, the complexity wise, if you see, very small in size, and if we have a number of components which are designing together as fabricating together, the cost of these will be very low, and comparatively this is taking power consumption which is very less, and highly reliable model, and comparatively with BJT you can say it is operating speed is high, and instead of using number of connections we can go ahead with simple integrated circuit that makes the reduction of number of wires so that it can be useful for further use, and easy to use, simple in design. Then these are the advantages. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.